Hello everyone, this is Ms. Bonk. We are going to do some rotational dynamics examples. So if you missed class, this is what we did in class. And if you just need to refresh your memory a little bit, this might be helpful too. All right, so we are talking today about torque. We are talking about torque in two senses. We're using our definition of lever arm multiplied by force, and we're also using our Newton's second law equation for rotational dynamics, which is torque equals I alpha. So for this first one, we're going to be tackling this problem from like the lever arm force perspective. So let's take a look at this. It says we have this figure that shows your ankle joint and the Achilles tendon is attached at point P there. The tendon exerts a force of magnitude 720 newtons. Determine the torque, so they want magnitude and direction, which we'll have to keep in mind at the end, of this force about the ankle joint, which is located 3.6 times 10 to the negative second meters away from point P. So let's make a list of our givens, and then I'm going to redraw this picture a couple of times just so that we can make sure we are all on the same page. So in terms of our givens, we know that the force that the tendon is putting on the ankle joint is 720 newtons. And then we have this distance. So this is not our lever arm. This is just the distance from our ankle joint to that point P where the tendon is actually making contact and applying a force on the joint. So I'm just going to call that a distance D for now. 3.6 times 10 to the negative second meters. We are trying to solve for the torque. So they give you this picture at the bottom, which I think is helpful. I'm going to redraw that a little bit bigger maybe so it's easier to see. So we have this ankle joint that's on the right. And see how the problem says find the torque about the ankle joint? That pretty much means use that ankle joint as the axis of rotation. So I have my ankle joint here. That's going to be my axis. Then I have that point P where the tendon is attached, a distance D away from the joint it says. So let's just draw a line. This will be our point P. We have this distance that is 3.6 times 10 to the negative second meters. And at that distance, we have, sorry, I have the hiccups, our force being applied. So that's our 720 Newton force. Now, what we cannot do is just say, oh, torque equals R perpendicular times F. So that's 3.6 times 10 to the negative second meters times 720 newtons. No. Why can't we do that? Well, because remember that lever arm, this R perpendicular in this equation, that is the perpendicular distance from your axis to your line of action, or essentially your force. 3.6 times 10 to the negative second, that distance there is not perpendicular to the force. That blue line is not perpendicular to that red line, right? So we need to solve for our lever arm, which is our perpendicular distance from the axis to the line of action, or the extension of our force. So before we solve for the torque, we need to solve for that lever arm. And it might be hard to see, but they do give you an angle in that diagram on the bottom left. Let's see, I'll do green. This angle is 55 degrees, they tell us. So we are going to use the equation torque equals R perpendicular times F. We know F, we need to solve for R perpendicular, which is that orange dashed line or yellow dashed line in the diagram. So how do we solve for R perpendicular? So remember, one of the key things is that this lever arm is perpendicular to our force. So we know we have a 90-degree angle there. And we're going to have to use trig. And in case it's helpful, I will redraw this triangle rotated. So I have my red side I have my yellow side. That is a 90-degree angle. And then I have my blue side, which is that distance that they gave us. Oops, sorry. And this we know is 3.6 times 10 to the negative second meters. The other side, or that yellow side, is our perpendicular. Oh no, that you cannot read. Okay, so that orange side is our perpendicular. That's what we're trying to solve for. And then just be careful with your angle. When you rotate, sometimes it's hard to see where your angle is, but that angle would be 55 degrees right here. So let's solve for our perpendicular. Take a second and think about which trig function would you use to solve for that. If it helps, you can think of this is our opposite side, this is our adjacent side, this is our hypotenuse. So I'm going to use cosine. So the cosine of 55 degrees would be equal to my adjacent, so that's our perpendicular, divided by my hypotenuse, which is 3.6 times 10 to the negative second meters. So to solve for our perpendicular, I have to multiply both sides by that 3.6 times 10 to the negative second meters. Make sure your calculators are in degrees, not radians, otherwise you will not get the same answer. And I think you get something like 0.0206 meters. And we're not done yet, but we know our lever arm. So we know everything that we need to know in order to calculate the force about that ankle joint. So our last step then is to plug that into our equation. So we have torque equals. Now really in my calculator, I would just plug in 3.6 times 10 to the second times cosine of 55 times 720. I wouldn't plug in this rounded value, but for the sake of doing this example, I will. And when you do that, you get about 14.9. In units, we have newtons times meters, Newton meters. So that's the magnitude of our torque. But it also asked for our direction. So we have to think about, here's my axis, right? That's my axis. So think about that almost as a hinge. And this force is pulling on that ankle joint this way. So think about, is your ankle going to rotate clockwise or counterclockwise? That would cause clockwise rotation, right? If I have something with a hinge on the right and I'm pulling up and to the right like that, my ankle will rotate clockwise. And remember that when we're doing rotational, clockwise is the negative direction, counterclockwise is the positive direction. So technically our answer for torque needs to be negative. Let's do an equilibrium example. We will do more practice with this this week, but let's do one now. I would say that in the rotational unit for AP Physics 1, equilibrium problems may be the longest problems that I typically see because there's a lot of front loading of conceptual ideas that you need to get down before you can plug in your numbers. So let's do one now so you can get the idea and start applying some of these concepts. So it says a woman whose weight is 530 newtons is poised at the right end of a diving board with a length of 3.9 meters. The board has negligible weight, we'll talk about that in a second, and it's bolted down at the left end while being supported 1.4 meters away by a fulcrum. Find the forces F1 and F2 that the bolt and the fulcrum respectively exert on the board. Okay, so if we're listing our givens, I called the force of gravity on the woman, in other words, her weight, I just called that FW. You can really call it whatever you want, but we know that that is 530 newtons. Technically, it's negative because it's pulling down. And let's see, in the diagram here, they call that capital W for her weight, whatever you want to call it. It's the force of gravity on the woman. And then when it says that the board has negligible weight, they're kind of doing us a favor there. They're saying, don't worry about the force of gravity on the diving board. So that's one less force we have to worry about. You may have an equilibrium problem, or you may see equilibrium problems, or you do have to take into account the force of gravity on the item that can possibly rotate. But for this, they said, don't worry about it. And then in the diagram down here, they have a cursive L. Remember that sometimes textbooks use a cursive L for lever arm instead of R perpendicular. So they said LW. That's the distance the woman is away from the axis. They have the axis on the left here, which we'll talk about in a couple minutes. LW is essentially then the length of the board, so 3.9 meters. And then they call it L2. I'm going to call it LF for the distance the fulcrum is away from the axis. So you could call it L2 if you want. It's the distance that force 2 is away from the axis, whichever you prefer. And then if you're wondering what a fulcrum is essentially a support, and it's often shown or depicted as a triangle. So you could say, oh, what if I have a seesaw, like at a playground, and I have, a kid on the seesaw? They'll use a fulcrum as the support there. So that's usually the symbol you'll see for it, and it's just another word for a support, essentially. So let's take a look at this diving board and what's happening. We have this bolt here on the left, we have the fulcrum here, and then we have the woman on the far right. Underneath that diagram, they have a free body diagram. So the bolt is actually holding the diving board down. So you have that F1. That's what one of the variables we're trying to solve for. You could call that bolt force in case you forget which one that goes with. So that is holding that end of the diving board down so that it doesn't rotate upwards. And then we have our fulcrum force, our force from that support, F2, that we're trying to solve for, and that's holding the diving board up. So those are the two forces we're trying to solve for. We know how far away our fulcrum and our woman are from the axis. And since this is an equilibrium problem, that means that our object is not rotating. It has no angular, or at least what that means is it has no angular acceleration and it has no linear acceleration, is maybe a better way to say that. So that means three things are true. First, sum of the forces in the x direction have to equal 0. Second, sum of the forces in the y direction have to equal 0. And third, and this is the new part, sum of our torques have to add up to equal 0. In other words, all of our forces are balanced, all of our torques are balanced if our object is at equilibrium. Looking at our free body diagram, there are no forces in the x direction. So yeah, the sum of the forces in the x direction is 0. There aren't any forces in the x direction at all. Let's write out some of the forces in the y direction. So if you recall from last semester, I usually start with my positive forces. So up is usually the positive direction force. So I have F2, and then I subtract any negative forces. So minus F1 minus I called that FW, the force from the woman. Those have to add up to equal 0. And I want to solve for F2 and F1. But if I just stop here, I'm going to be stuck because I have one equation and two unknowns. So this is where the sum of the torques will come into play, our new aspect of problem solving. So if I write out sum of the torques, I know that they have to add up to equal 0, But we have to do a couple of things here. We need to look at our diagram and identify our axis, which this problem actually already did for us. So they said, okay, let's put the axis where that bolt is. And the thing about equilibrium problems, especially if you have multiple forces that are unknown, is you want to be strategic about where you set your axis. Because if a force is going through your axis of rotation, it's not causing any rotation. So the torque due to that force will be zero, which is helpful if you have multiple forces you don't know. Because if I set the axis here on this force I don't know, I only have torque due to F2 and the weight of the woman. If I set the axis here on F2, that force is going through the axis, so it's not causing any torque. So I only have torque from F1 and the weight of the woman. I wouldn't want to set my axis where the woman is, because then I would have two torques, and I don't know either of those two forces, so I would get stuck again, and I would have one equation and two unknowns. So let's go along with the fact that the axis is on that bolt. So the bolt is not causing any torque in that case. And before I write it out, it's helpful to think about, is F2 causing clockwise or counterclockwise rotation, or attempting to? And is the woman's weight attempting to cause clockwise or counterclockwise rotation? Because that will tell me how to write out some of the torques. So think about, if this is like my hinge here, this axis, and that fulcrum is pushing up, that would be counterclockwise rotation, which is positive. Remember, the board's not actually moving, but this is the direction of rotation that these forces are attempting. And then the woman's weight is pulling down, which would be the clockwise direction. So that's going to be a negative torque. So going back to my sum of the torques equation, I could say like the torque caused by F2 minus the torque caused by the woman has to equal 0. And here I substitute in my equation for torque, which is R perpendicular times F. And thankfully, these forces are perpendicular to the diving board, so we don't have to worry about doing any trig or anything. So the torque caused by that F2, that's going to be the distance from the axis to F2, which is 1.4 meters, times F2, minus the torque caused by the woman would be her distance from the axis, which is 3.9 meters, times FW, which is 530 newtons, which has to add up to equal 0. So I can solve for F2. It would be equal to 3.9 times 530 divided by 1.4 meters. I get F2. I want to say it's 1464 something. Let's see. 1476.4. So 1476.4 newtons. And F2 is pointing upwards, so we'll keep that positive. So again, at this line here, I'm substituting in this equation for your torque. It's your lever arm times your force. And see, now I know what F2 is now. Sorry. So if I go back to my sum of the forces in the y equation, I had one equation and two unknowns, but now I know F2 and I know the force of the woman. So I can solve for F1. If I add F1 to both sides there, I would have F2 minus FW, and now I know that's 1476.4 newtons minus 530 newtons. And I get F1 is 946.4. And I just have to be careful because that F1 is pointing downwards, which would be the negative direction. So equilibrium problems, like I said, they have a lot of front loading where you have to do a lot of conceptual work beforehand. But you can always start with the forces and the torques being balanced. Look at your free body diagram. Think about what's causing torque, in which direction, where you're going to put your axis, and just take it step by step. And we'll do more of these later this week. All right, so let's do a problem that uses the rotational version of Newton's second law. So this says a uniform solid disk. So remember that we mentioned something called moment of inertia last week, and moment of inertia depends on an object's shape. So we are going to want to start paying attention to any information we get about the actual shape and size of an object. So in this case, we have a solid disk of mass 24.3 kilograms with a radius of 0.14 meters. It's free to rotate about a frictionless axle. Forces of 90 newtons and 125 newtons are applied. So first we are trying to solve for the net torque. Same thing as sum of the torques. And then for part B, it wants to know what's the angular acceleration of the disk. So we're looking for alpha. All right, so let's start with our net torque. So we're going to use this pivot point here, this center point of the disk as our axis. That's where like the axle is attached anyway, so that makes sense to do that there. And when we're trying to solve for net torque, similar to what we just did in the other problem, we want to think about whether or not the forces that are being applied are causing clockwise or counterclockwise rotation. So thankfully, they are at 90-degree angles to the actual object, so the forces are tangential to the object. So we don't have to worry about doing any trig or that R F sine theta aspect of the net force or torque equation. But let's take a look at what direction these forces of rotation these forces are causing. So remember our axis is in the center. Take a look at that 125 Newton force. Think about someone taking their hand and like hitting this disc that way to the right. Would that cause clockwise or counterclockwise rotation? So that's going to cause clockwise rotation, which remember is the negative direction. And then think about, remember, this thing is free to rotate. It's frictionless. Take your hand and smack that thing this way. On the bottom there, if you hit it to the right, it's going to rotate counterclockwise, which is going to be positive torque. So I would write this as like my net torque is the torque from the 90 Newton force minus the torque from the 125 Newton force. And that's what we're trying to solve for. We're not going to set this equal to 0 because think about if you have 125 Newton force at the top, 90 Newton force at the bottom, and they're causing rotation in opposite directions, they're not balancing each other out in this case. They're the same distance away from the center. It's being pushed harder in the clockwise direction than the counterclockwise direction. So we're not going to say that our sum of our torques or our net torque is 0. This object is accelerating. It has angular acceleration, and that's what we're solving for part B. So these should not equal, the net torque should not equal 0. So the net torque caused by that 90 Newton force, that would be the distance from the axis times that force. And that distance is just the radius of the axis, which they told us is 0.314 meters. So when I'm solving for the torque from the 90 Newton force, that's going to be 0.314 meters times 90 newtons minus the torque from the 125 Newton force. So that is it's also the same distance away, just the radius, 0.314 meters times 125 newtons. And that should equal, I want to say 11 off the top of my head, just from memory, but I may be wrong. So let me just check. It is, yeah, negative 11 Newton meters. So does it make sense that our answer is negative? So that's saying that the net torque is in the negative or clockwise direction. It is being pushed harder clockwise. So at the same distance, each force is the same distance from the center. So yeah, it makes sense that overall it's going to spin clockwise in the negative direction. So that checks out. All right, part B. So part B is asking for alpha, the angular acceleration. And this is where now we're going to use Newton's second law for rotational motion, which says that alpha is equal to your net torque divided by I, your moment of inertia. So remember, this is like saying acceleration equals F over A, Newton's second law from last semester. But this is the rotational version. So we know that the net torque is negative 11 Newton meters. And we need to figure out what that moment of inertia is. And this is where we need to look at what shape, what type of object do we have? We have a disk. So the moment of inertia, sometimes called rotational inertia for a disk, and this is something you can look up in your notes or your textbook or search it. It is 1/2 mr squared. Helpful to know off the top of your head. Okay, so in the denominator we have 1/2 times m, which they told us was 24.3 kilograms, times the radius, and don't forget to square just the radius in that denominator. And I want to say this is negative 9.2 radians per second squared. I will double check that. Yep. So it's accelerating clockwise at 9.2 radians per second squared. All right. So the next problem, what I would like you to do is let me read it. We can maybe highlight any important pieces of information. And then take some time, maybe pause the video and try it on your own before you look at my work. It's very similar to the one that we just did, so you should be able to handle it, but it would be good to practice this on your own. Okay, a solid cylindrical disc. So again, we have, oops, that's not what I wanted. Again, we have a disc. So keep that in mind if you need moment of inertia. It has a radius of 0.15 meters. It is mounted to an axle that is perpendicular to the circular end of the disc at its center. So this is like the same scenario we had in this problem where we have a disc, it has an axis that is perpendicular to the disc through its center. When a 45 Newton force is applied tangentially to the disc, so again, that would look pretty similar. The force that's being applied is just tangent to the surface of the disc. Perpendicular to the radius, the disk acquires an angular acceleration of 120 radians per second squared. And you are tasked with finding the mass of the disk. So I would take a second, pause it, list your givens, think about what equations you have, try to solve that on your own. All right, so hopefully you tried that on your own. Let's go ahead and list our givens and go through this, and you can check your work, make sure that you got the same answer. So we have radius is 0.15 meters, force is 45 newtons, alpha is 120 radians per second squared. It's a disk, which means the moment of inertia is 1/2 mr squared. We are looking for mass. So let's take a look at torque equals I alpha. Second law for rotational, solve that for, or I guess what you could do, so many different ways, orders you could do this in. So you could just go ahead and plug in 1/2 mr squared. And now solve this for m. So multiply both sides by 2. And then divide by r squared alpha. So I get mass equals 2 times torque divided by r squared alpha. So let's plug in what we have. So that means my mass is equal to 2 times. So do we have torque? Torque is not in my list of givens here. So torque is equal to r perpendicular times force. And they told us the radius was 0.15 meters and the force was 45 newtons. So you kind of have to solve. You could substitute that into your expression before you plug in numbers if you want. That's fine. You get 6.75 Newton meters. They didn't give us a diagram. They didn't tell us what direction the rotation was, so I'm just assuming positive, which is totally fine. So I have 2 times 6.75 Newton meters divided by r squared, so 0.15 meters, that is squared, times 120 radians per second squared. And I get my mass equals 5 kilograms. A nice whole number. So hopefully you're able to get that on your own. If not, of course, feel free to ask me questions. So notice we have two equations for torque. We have the second law, I times alpha, and then we have the other definition, which is lever arm times force, and we had to use both in this case. One more conceptual example, and we are good to go. Okay, so one kind of conceptual type example to end our examples today. It says a certain torque acts on an object to rotate it about an axis, causing the object to move with angular acceleration of 5 radians per second squared. In a second trial, 2 changes are made to the parameters of the experiment. So first, the axis is shifted so that the object's rotational inertia is halved. Rotational inertia is another way to say moment of inertia. And the second thing that they change in the second trial is the torque acting on the object is also decreased to half of its original value. And we want to know what's the new angular acceleration? What's the angular acceleration of the object during this second trial? So there are a couple of ways to think about this. I think maybe it'll be useful to look at it in terms of numerical values first. So let's just make 2 lists. We have our first trial. A lot of the times in physics, it's helpful to make a list. Think about what your 2 objects, 2 scenarios, whatever it is, have in common with each other. So we know that in the first trial, the angular acceleration, alpha, is 5 radians per second squared. And they don't tell us anything else. But what I can do is I can think about what has to be true of the torque and the moment of inertia in order to get 5 for alpha. So remember that Newton's second law for rotational says that alpha equals torque over moment of inertia. Net torque, really. I'm going to leave that out for the sake of simplicity right now. So I can make up any number for torque and any number for moment of inertia in the first trial as long as I get 5 for my alpha value. So let's just say to start off that maybe torque was 20 Newton meters and the moment of inertia was 4 Newton meter, or sorry, that would be kilogram meters squared. 4 kilogram meters squared. Okay, so let's just check that and make sure that we would get an alpha of 5. So alpha is equal to torque over moment of inertia. That would be 20 Newton meters divided by 4 kilogram meters squared. And we would get 5 radians per second squared. So you could pick any numbers as long as you divide them and you get 5. I just picked 20 and 4. Okay. The reason I did that is because now I have numbers to actually manipulate for the second trial. And in the second trial, it said that the torque and the moment of inertia were halved. So instead of torque equals 20, we're going to have torque equals 10 Newton meters. And instead of moment of inertia equals 4, we're going to have moment of inertia equals 2 kilogram meters squared. So then if we go ahead and see what will our new alpha value be during the second trial of this experiment, I'll have 10 Newton meters divided by 2 kilogram meters squared. And I get an alpha of 5 radians per second squared. So my angular acceleration stays the same. I started at 5 radians per second squared, I ended at 5 radians per second squared. And really this just boils down to the relationships between our variables in this equation up here. And you could really look at this without making up numbers and do it pretty quickly if you're comfortable with looking at the relationships between variables. So I have alpha equals torque divided by moment of inertia. So let's say I keep I constant, and if I cut torque in half, that's going to cut alpha in half. That's a direct relationship. So I'm cutting torque in half, that's going to cut alpha in half. Now let's look at what happens when I manipulate I, moment of inertia. So if I keep torque constant, I'm not changing that. If I cut I in half, I'm decreasing my denominator, which increases my fraction overall. So if I cut I in half, I'm actually doubling my angular acceleration. And in this case, we cut both torque and moment of inertia in half. So I cut torque in half, which cut alpha in half, but then I cut I in half, which doubled alpha, which gave me the same value for alpha as I had in the beginning. So I really didn't do anything to the angular acceleration with those two changes for trial 2. Okay, let me know if you have any questions, and I will see you in class.